Hello everyone, this is Dr. Nimish Kumar Srivastava, Assistant Professor in Kumar Engineering College in the Department of Electronics and Communication. So in this lecture video series of optical communications, we were discussing about the various modules that in together they are going to form an optical receiver. So we have discussed each and everything in details about how they are going to affect the performance of the system. Now in this lecture we are going to discuss about what is the sources of noise which is associated with the optical receivers. So now this optical receivers, the different noise that is possible going to affect the performance of the system is, we will discuss it with the help of this block diagram. So this is the entire block diagram that will show that what are the different noises that is going to affect the performance of the system by degrading the original version of the strength of the original version of the signal. So basically we will see what are the important noise. First one we will see about the thermal noise. Then apart from that we will discuss about the dark noise, then short noise. So these are the main three culprits that are going to degrade the performance of the system by corrupting the original version of the signal. So we will see all those things in detail. So let us try to move into the theory about that. So we have discussed that three main culprits are thermal noise, then we are having a dark noise, and apart from that we are having a quantum noise. We can also treat it as a short noise. This quantum noise we can also write it in place of that as a short noise. So what is the meaning of this thermal noise? This is basically a fluctuation, that is a spontaneous fluctuation due to the thermal interaction between the free electron and the vibrating ions in conducting medium, and it especially this is more dominating in the resistor at the room temperature. So if suppose that the thermal noise current is denoted by IT, then in a resistor R, then it can be expressed as that the mean square value of that thermal noise can be expressed as IT square, which is 4 kTb by R. So where K is your Boltzmann constant, T is the absolute temperature, and B is the post detection bandwidth of the system. Now this assuming the resistor is in the optical receiver. Now the next current is the next noise which is related to the detection process is your dark current noise. Now when this dark current noise is going to inculcate in the receiver portion is when there is no optical power incident on the photodetector, a small leakage current still flows through the device terminal. This dark current contributes to the total system noise, and it gives to a random fluctuation about the average particles flow of the photocurrent. So therefore this can be written as, this dark current can be written as ID square bar, which is equal to the twice of E BID. Now ID is the dark current and E is the charge on the electron. The next thing is about the short noise. What is the meaning of short noise? Short noise, whenever suppose the ideally and input optical power is constant, now which implies that on an average the number of photons per unit time does not vary, but this is something ideal case that not happens in actually. So but in the fact that the actual number of photons arriving at a particular time is unknown, and so is a completely random process. Hence the number of photo generated electrons at any particular instance is random in nature, which you can say that it is a random variable. So in addition, the number of electrons producing photocurrent will vary because of their random recombination and absorption. So generally the actual number of electrons are not exactly same as the average number of electrons, which contributes to noise which is known as the short noise. Now thus the photocurrent produced by a constant incident optical power signal can be expressed as IT equals to IP plus of IST, where IP is equal to R into P in. P in is the input optical power. Now this signifies this IP signifies the average value of the photocurrent produced, and the IST, which is the that is the small I and the subscript S, it is the it represents the variations in the photocurrent due to short noise, and it may be noted that the spectral density of short noise does not change at all. So we can say that a short noise resembles the white noise whose spectral density does not depend on the frequency. It's varies constantly. So there is no, even though you are varying the frequency, but its variation is not, that means it is not varying with respect to the frequency, it will remains constant. Now this dark current ID also generates some noise, that is the short noise. So in fact the dark current represents the value of the photocurrent which is produced even in the absence of an incident optical power. The surface leakage current and currents due to the generation or the recombination of electron hole pair within the depletion region even in the absence of incident optical power contributes to the dark current in photodetector, which in combined form which will be expressed as IT equal to IP plus of ID and plus of IST. We know that IP is the photocurrent and ID is the dark current, and what is this IST? We have already discussed here. IST represents the various variation in the photocurrent due to the short noise. So this is the total combinations of a current which in totality form totally they are going to leads to a generation of a short noise. Now what is the RMS value? What is the RMS value of the short noise current which can be expressed? So it can be written as twice under root of twice of Q IP plus of ID. Now there is another noise which is associated with this photodetection process, which is your I by F noise. So a photodetector or photodiode also generates another type of noise that occurs in complete darkness, that is in the absence of the any photon, in the absence of any optical power. Now this is other than the dark current noise in photodetector, which is known as I by F noise. Its RMS value per bandwidth is something which is inversely proportional to frequency, which can be expressed as IFN, which is equal to K 1 upon F I to the power alpha divided by FB, where thus this all the constant I, the K, alpha and beta are found empirically, and whose value is alpha value is approximately 2, beta is approximately between 1 and 1.5. Now this is the noise which is important only in the low frequency range and can be neglected when modulating frequency is much greater than 100 Hertz. Now this is the figure which is depicting a equivalent circuit of a noise in a photodetector. Equivalent circuit of a noise in a photodetector. So as per this figure, it may be noted that each noise component is an independent random process which is approximated by the Gaussian statistics, and the overall noise is given by I noise, which is equal to under root of IS square plus ID square plus ITH square plus I 1 by F square. So this is all the square term which is combined, and then we are taking the root of that. Now this signal to noise ratio is, we know that is one of the important performance parameter which is the deciding factor of any device, whether the signal received by the device is in proper having the how much the there is a degree of a corruption in that particular, I mean how much to extent that noise is affecting that signal. Now this I, that is SNR, which is given to the average signal power, the ratio of average signal power to noise power, which is something written as IP square upon I noise square. This we know that IP is equal to R P in, which is the response in terms of a responsivity R. So which is can be expressed as, we are just putting down the value of IP as R P in, so it will be R square P in square upon I square noise. So this is the signal to noise ratio. So as we have already discussed earlier that it is the thermal noise that contributes maximum to the overall noise present in a pin photodiode, and which can be expressed as by this formula I noise square. If you are neglecting, suppose that if we are neglecting all the other terms except the thermal noise terms, so the signal to noise ratio will be limited by the thermal noise given by SNRTH which is equal to the R square Pn square upon Ith square. So instead of I noise square, we have already equated this through only thermal noise, which is predominating all the other types of a noise which is present in the detection process. Now next thing is, if you are substituting this Ith value, then we will get this signal to noise ratio as this portion. If you are just substituting the value of Ith, we have already discussed in the very previous slide about what is the strength of the, that means the noise power related to the thermal noise, how we can express the mean square value of the thermal current that contributes to a thermal noise. So if you are just substituting that value, you will get the signal to noise ratio of the thermal noise, where this BWPD represents the bandwidth of the photodetector. The thing is that if you want to reduce this thermal noise and its influence on the signal to noise ratio, because this is the thermal noise which we have assumed that it is most predominating form of noise, and if you want to reduce the effect of this thermal noise and its influence on the signal to noise ratio, or the load current or the load resistance RL should be increased, because this load current is something which is inversely proportional to the Ith. So if you are increasing the value of this RL, then we are decreasing the thermal noise current. So in order to reduce that, we are increasing the RL, and if we wish to quantify the effect of a thermal noise, then we can define a term which is known as a noise equivalent power, which is the minimum incident optical power per unit bandwidth, and so as to give unity value of a signal to noise ratio, which can be expressed mathematically as noise equivalent power is equal to the ratio of input optical power to under root of bandwidth of the photodetector. So this is the formula associated with this. So, but by definition, the optical receiver parameter detectivity is the inverse of the NEP, that means noise equivalent power. Now the next thing that we are supposed to discuss is about the optical wireless communication system. These are the two, basically two different field which are combined. If we are combining this optical as well as the wireless medium, so that comes under the part which is known as a radio over fiber, right? Because it's not possible to just lay down the optical fiber to the hilly areas. In the hilly areas, not possible to just lay down the fiber just by cutting all those huge mountains. For that case, we have to move to a wireless medium. So if we somehow combining these two different areas together, then we are harnessing both the advantages of both the different areas, and we can efficiently utilize their advantages to transmit our information at a farther distance, even between two continents. That can be possible if we are combining these two areas of optical as well as the wireless communications. So this is the future, and at present we are going through this. It's still the researches that is going on in this area of radio over fibers. Various improvements are going on. So the example of this optical wireless communication medium or system is optical, that means which is also called as FSO, fiber space optics, or the radio over fiber communication. Now the optical wireless communication refers to the transmission in unguided propagation media through the use of optical carriers, that is in visible, infrared or ultraviolet bands. So it is an optical transmitter and receiver system with wireless channels. So this optical wireless communication is also called as FSO, which is known as free space optics or free space optical communication. Now this provide the advantages of both the optical as well as the wireless system. Now this is the typical model of a optical wireless communication, right? We have an optical transmitter as well as we have an optical receiver, but the medium that we are using for transmitting the information, for transmitting the optical carrier, the signal, is the wireless medium. Now this is also the same block diagram. That means somehow whatever the data that we electrical data that we want to transmit, we are first modulating that data, and that modulator, generally that modulator that we are using, that means as an external modulator, that is your lithium niobate external modulator. It could be it comes under a single drive or even in a dual drive. Dual drive is basically used to it is used to overcome the demerit which is caused by the effect of a chirping. So in order to nullify this effect of a chirping, one have to move to a dual drive Mach Zehnder modulator, and it is this dual drive Mach Zehnder modulator which is just by controlling the biasing voltage of that electrodes of the dual drive Mach Zehnder modulator, one can play between whether he want to transmit the even order sideband of the optical carrier of the modulated signal, or he want to transmit the odd order sidebands of the output optical signal. So this even and odd order sidebands, whatever we want to transmit that, and if you are following it on the photodetector, then you will see that we know that our photodetector just heterodynamic process that is going on at the photodetection process, and which will generate the difference between that two even order sidebands or even odd order sidebands. If suppose that I am having a first order sideband, that means FM and minus FM. So whatever the electrical equivalent signal that will be generated after the photodetection process, that will be 2 times the FM, that is 2 times the frequency which is driving this modulator. So this optical, that means this external optical modulator, with the help of this one can do the frequency up conversion. Like if you want to transmit the 4 times the driving signals, suppose that I am driving my modulator by a 5 gigahertz and I want to get the output frequency at 20 gigahertz. So that can be easily done by using a controlling the driving voltage of the optical modulator. So you must be having a drive circuit which is used to drive the laser. Also apart from that, we are having this modulator also driver provided, so that whenever we are feeding the optical carrier through the drivers, that means, or we are feeding the this RF signal to the electrodes of the external modulator, that should be it should be controlled version of the strength of the signal that we want to transmit. So this thing is given to the LED or laser, and this LED or laser will generate the optical version of the input signal, and this will given to the after getting the original version of after getting the optical signal, it will be passed through the given to the receiver by using a medium which is known as the wireless medium. So after this, the thing is that this is combining the effect of both the things versions. So these are the advantages of the free space optics, and that means that is what are the advantages, that these systems improves the system capacity and throughput support, as well as it is having a high data rate, so as well as the high security, because we know that the optical fiber is something, communication medium is highly secure, because it is not easy to tap the original signals or the optical signal from the various layers of the various layers of the jacket that is covering the clear core and the clad. It's not very easy to just tap that optical signal back. So and that is having the high security and performance capabilities. Purchase of a spectrum is not required, and have good reliability and much lower cost of installation as well as the operating the system as compared to the other technologies. This FSO, that is the optical wireless communication, also offer a design alternative for the extremely challenging aircraft to aircraft and aircraft to satellite vehicular communication scenarios. The third advantage is that it can be used for short distance as well as for long range applications. Now the main applications. What are the main applications of optical wireless communications? So these are the main applications. That means this FSO, optical wireless communication system, can be used for high data rate communication between two fixed points. over distances up to several over distances which can vary to several kilometers. Now they are appealing for a wide range of applications such as MAN, which is a metropolitan area network extension, local area network, that is a LAN, LAN to LAN connectivity, fiber backup, backhaul for wireless cellular networks, disaster recovery, high definition TV, and medical imaging, even video transmission. Apart from that, wireless video surveillance, monitoring, and quantum key distribution among the others. The third main application is military applications and space application, including the inter-satellite and deep space links and vehicular communications. Apart from that, it is also used in visible light communication. It can also be used in 5G wireless networks. Also, it can be used in places where laying down of fiber is not easy. We have already discussed this point, that we are combining these two areas of the optical and the that means wireless, because it is not possible to just lay down the fiber in every areas, in every situations. It's not possible to just dig the whole complete the hilly areas and to lay down the fibers. It's not possible. So for that, we are combining this optical wireless. We are using this optical wireless medium. Now what are the challenges that is associated with the optical wireless communications? So the main disadvantage or main limitation for optical wireless communication is its disappointing link reliability, particularly in long ranges due to atmospheric turbulence, induced fading, and sensitivity to weather conditions. Second is the optical power launched from the transmitter is affected by various factors before arriving at the receiver, and these factors include the system loss, geometric loss, misalignment loss, atmospheric loss, and atmospheric turbulence induced fading and ambient noises. Now the performance, how we can improve the performance limitations and how we can remove the limitation and improve the performance of the optical wireless communication. There are various factors. First one is channel codings. With the help of channel coding, we can improve the performance. Then spatial diversity. Apart from that, adaptive transmission, then relay assisted communication, hybrid RF or FSO system, and coherent FSO systems. So these are the various techniques that we can use to enhance the performance of the optical wireless communication. So this is all about the various topics that is related to the optical communication. We have discussed each and every topic in details, and we have covered all the unit of your optical communications. So thank you all for watching this video.